last turn we started the magnetic measurements. In this case, first topic was separation of iron loss. Yesterday we discussed what is iron loss and what are the two components of the iron loss, and how can we um, basically um, means main thing I was discussing on the last turn yesterday, that when we measure in transformer, through transformer open circuit test, we measure the iron loss or the core loss. Iron loss and core loss is the name of the same loss. Then we measure as a core loss. In the open circuit test, whatever is the wattmeter reading, it is basically the core loss or iron loss together. And you must have uh, there is no need to, because in that case we measure just to find out the efficiency of the transformer. So in that case we are not required to separate these two losses. And somewhere it is required to we are required to separate them, but do you remember anywhere you are required to separate the iron loss or core loss into the hysteresis and eddy current loss somewhere in the machine? Do you remember? You must have studied circle diagram of induction motor. Do you remember? You studied circle diagram?
Sir, three phase induction or one phase?
Three phase, three phase. Have you studied it? You must have
Yes,
studied
sir.
it. So
Yes, sir.
in
Yes,
that
sir.
case, you are required to. There is a straight line that that represents the losses, and over there you are required to divide the core loss into two parts, eddy current and hysteresis loss. But at that time you must have assumed, it is assumed over there that it is half half over there, but there is no, till now you didn't study how can we separate them, means as per their quantitatively, you can say, accurately. So here there is a technique through which we can separate iron loss into the hysteresis. It's two components, hysteresis and the. So this is the formula you must have studied earlier also, that hysteresis loss is equal to, it is basically directly proportional to the frequency. This is a constant, and the flux density to the power uh, something which is called Steinmetz index, and this is your material dependent. Steinmetz index is material dependent. So you can see that the hysteresis loss is directly proportional to the flux, and your Steinmetz constant times flux density. And as far as eddy current loss is concerned, it is directly proportional to C and square of the your flux density, and T stands for thickness of the laminates. So it is also directly proportional to K. So this is and this is also proportional to the form factor, apart from the eddy current, constant form factor of the means, as the waveform is sinusoidal, then eddy current loss will be something, and if it is not non-sinusoidal, then because form factor will change. Whereas the hysteresis loss does not depend upon the form factor at all. So this is in brief. Now you can see that if you look in these equations, if I'm considering that here, this is very important point you should note down. We are considering that the flux density in the core, whose flux whose loss we want to separate, iron loss we want to separate, is constant here. So only variable is frequency. In this equation also, everything is constant, especially flux density is also constant, only frequency is varying. So these two equations we can write in this form. Total means iron loss is equal to, this is your hysteresis loss and this is your eddy current loss. If anybody is having any question regarding this expression with reference to these two equations, you can ask, please.
Sir, one eddy current loss is
जी जी बोलिए, थोड़ा सा थोड़ा तेज बोलिए, यू आर नॉट प्रॉपर्ली ऑडिबल टू मी. हाँ बताओ.
yes sir. थोड़ा सा कफ एंड कोल्ड. Sir, sir, eddy current और loss of hysteresis loss में sir, सर जो मैक्सिमम मैग्नेटिक फील्ड रहता है सर, वो
फिर
उसका
यार तुम्हारी
प्रोपोर्शन.
आवाज बहुत कम हो गई.
अच्छा ओके सर, हो गया तो अब छोड़ दीजिए सॉरी
क्या हो गया?
सर. नहीं मतलब सर वो थोड़ा कफ एंड कोल्ड हो गया सर.
अच्छा तुम पूछ लो, मैं ये कहना चाह रहा हूँ. ये इसमें देखिए, एम में सारे कांस्टेंट्स आ गए, एन में सारे कांस्टेंट्स आ गए. वी आर अज्यूमिंग ऑल अदर पैरामीटर्स. एक्चुअली variable parameters are two, your your frequency and flux density. But here in this method, whatever method we are discussing in for separation of the iron loss, here we are assuming flux density also constant. So these two, then if we look upon this expression, then f is variable and all other parameters are constant, so they are clubbed together in m. Similarly here, only your frequency is variable and all the other parameters are constant, so we club together and in another constant n. So that's what I had written here. It is
ओके सर, थैंक
it
यू.
is written
यस सर,
also.
ओके.
You see, m is equal to this, n is equal to this. It is written also.
ओके
So
ओके सर, थैंक यू.
now we are dividing this equation by frequency. Now, if this is your iron loss per unit frequency, and then right side is coefficient, another coefficient, and frequency. So this equation, what do you I need your comment on this equation. What kind of equation it is, if we are talking about the this parameter and frequency?
लीनियर इक्वेशन है, स्ट्रेट लाइन.
It is a straight line. That is drawn here.
mx plus c.
Y is equal to mx plus c. So this, my point is that this is basically graphical method which is used for measurement of iron loss. So if we are having data points, and we plot data points, means the iron loss per unit frequency and frequency of a particular sample, particular core, which is magnetized. So if we are having a data point, we will plot those data points, then they will be a straight, we'll get a straight line. And now, because means situation is like that, this, you are performing experiment like open circuit test on a transformer core, and with the objective to find out the iron loss or the core loss. So you have given the rated voltage at the low voltage side, and high voltage side is open circuited, and then you measured the power consumed by this open circuit transformer, and that power then you will minus no load copper loss from the wattmeter reading. So whatever is remaining is basically the core loss or the iron loss of the transformer. And at different frequency you have done this. Keeping flux density constant means V by F. Flux density constant means V by F ratio constant, है ना? V by F ratio constant. मालूम है ना? V by F ratio मालूम है?
Yes, sir.
Yes, sir. Yes, sir.
If you are keeping V by F ratio constant means you are keeping your flux density constant in the core. And in this method, whatever method I'm discussing here, this is prerequisite that your flux density should remain constant. This is graphical method. If your flux density is not constant, or while performing the experiment, if you are not keeping V by F in means, because we are varying the frequency, we should vary the frequency keeping in the mind that V by F ratio should remain same. So accordingly, you should vary voltage also so that V by F ratio should remain constant, although we are varying the frequency. If we'll do that, then it will ensure that our core, the flux density in the core remains constant, and then we can use this method for, because otherwise you see this equation will not be correct. Your flux density is also variable, so flux density term will also come here. So this will be means a complex equation. It will be not you cannot not reduce it into the straight line equation. Then it must have another variable here. So it will be two variable equation. So here you have to make sure that that is a prerequisite, that your flux density should remain constant while you are varying the frequency of the supply. And to make means for this you have to keep the V by F ratio constant while varying the frequency. If this is all done and you are able to find out different data points to for means iron loss per unit frequency and frequency, then you will plot it. You will get this kind of plot, straight line plot. Now our objective here is to find out the iron loss and to the hysteresis loss and eddy current loss from the iron loss. So if in this equation, if we are able to find out these coefficients M and N, if if we are able to find out these equations, then we will be able to find out, because M is basically representing the hysteresis loss per unit frequency, and NF is representing eddy current loss per unit frequency. So from this, if you will correlate this graphical version of this equation and this mathematical equation itself, then this M is basically the intercept with of the straight line to the y-axis. So this particular thing is M, and N is basically the slope of this straight line. You take any 2 points on the straight line, you can find out the slope. And once you are able to find out M and N, then for particular frequency you can find out hysteresis loss, and you can find out eddy current loss. So if anybody is having any query regarding this explanation, this method, explanation of this method, whatever I have done right now, it is very important method. So you can ask, please. G.
In the expression of n, what is that kb?
What is
That kb, kf to the power
K?
minus.
K क्या है?
Sir, n is equal to kf
अच्छा,
kb.
KH is basically the constant in the expression, and KF is the form factor of the supply voltage waveform or resultant flux waveform. It is the form factor. Means in this case, in case of eddy current loss, if your waveform is changing, means it is not having harmonic, and if it is having harmonic, then your eddy current loss will be affected. Obviously, when the form factor is more, then your hysteresis loss will be more. Means harmonics ज़्यादा होंगे तो hysteresis loss ज़्यादा होगा. Whereas this is not the case in case of eddy current loss. In hysteresis loss is independent of this factor. Okay. What is the form factor of your sinusoidal waveform? What is form factor?
One.
कुछ भी कह दो तुम 1, 2, 3. If you don't know the form factor, then
2
how
by
can
pi.
जी
2 by pi.
2 by 5, 3 by 5?
Sir, 5 नहीं pi.
It is 1.11 for sinusoidal waveform. You must have studied form factor
Sir,
in
2 by pi बोल रहा था सर मैं. 2 by pi. 3.14. 2 by
what is form
3.14.
factor. 1 by 1.11 कह रहे हो, तुम कह रहे हो 2 by pi.
Yes sir.
2 by pi 1.11 कहाँ से हो जाएगा?
Pi by 2 root 2.
तो 1.11 हो जाएगा. होता क्या है फॉर्म फैक्टर? रेक्टिफायर पढ़ा आपने? Full wave rectifier, half wave rectifier. You must have studied form factor there. Now these are the fundamentals. Many questions are asked on these topics. You should find out what is form factor. Okay, all of you, because these fundamentals are missing, and these are, whenever, listen, you are learning the thing. Whenever some fundamental question I am asking or any other teacher is asking, and if you are not aware, you note it down, and then you find out, because everything is not taught in a one subject. So you try to find out. So ये form factor basically is dependent, means it tells basically that whether your waveform, quantitatively it tells that whether your waveform is sinusoidal or it is having other harmonics, means distorted sinusoidal, distorted. So that you should find out. So form factor, this is KF is form factor. So eddy current loss depend upon the form factor, but hysteresis loss does not. Anyway, that is not the main focus here in this, because these all are the constants. So they are together represented by another constant. Here also they are represented by another constant. Only thing is that how we are separating these two losses using this graphical method, and how we are getting this plot, and after getting this plot, how we are separating the iron and eddy current loss. If anybody is having question on these points, you can ask please. Okay. Whatever I have discussed, it is explained here. Now we'll solve one problem. Now you see, we are the two methods. You forget about the graphical method. You forget about it. If you are having this equation, and you want to find out the coefficients value, how will you able to find it out? One of the method is this graphical method, but what could be the other method?
If the points are available, we can solve the equation.
So
Yes.
two equations
Yeah.
and we can find
That's
the two
correct.
values.
That's correct. Means we'll solve the equation, and for that we require data points. Here also we require data point. So here we are solving graphically. Otherwise we have to solve an equation by having the data points. And this is a straight line. Obviously, two unknowns are there. So the two data point you require. Okay. So
Yes, sir.
now we are solving this equation. sorry, this example. Here you can see that in a loss test on a sample of iron laminations, the following results were recorded. At 50 hertz, 250 volt, total iron loss is 200 watt. At 40 hertz, 100 volt, total iron loss. So these are two data points. Okay. Calculate the AD current and hysteresis loss for the each test. Steinmetz index is 1. So in this case, you have to find out the AD current loss and hysteresis loss at 50 hertz and at 40 hertz, both the cases. Now, my question here is, can we use graphical method for this problem or for this set of data? Yes, please. ग्राफिकल मेथड हम यूज कर सकते हैं कि नहीं कर सकते? जो अभी हमने डिस्कस किया आपसे, इसको यहाँ लगा सकते हैं नहीं लगा सकते?
नो सर.
क्यों?
तो फ्रीक्वेंसी डिफरेंट है.
हैं?
तो फ्रीक्वेंसी डिफरेंट है, मे बी इसलिए.
क्या डिफरेंस है?
फ्रीक्वेंसी.
हाँ, तो फ्रीक्वेंसी तो डिफरेंट होनी चाहिए यार.
Sir, VYF is not constant.
यस, दैट इज करेक्ट. हियर फ्रीक्वेंसी तो भाई आप प्लॉट कर रहे हो ना, आप देखो एक्स एक्सिस पे हम फ्रीक्वेंसी ले रहे हैं, वाई एक्सिस पे आयरन लॉस पर यूनिट फ्रीक्वेंसी ले रहे हैं. फ्रीक्वेंसी तो डिफरेंट होनी चाहिए. दो रीडिंग कम से कम हमारे पास दो रीडिंग होनी चाहिए. ओनली देन वी आर एबल टू फाइंड आउट दिस. लेकिन पर्टिनेंट पॉइंट ये है कि ये इक्वेशन और ये सारी चीजें और ये जो ड्रॉ किया है, दिस इज वैलिड ओनली व्हेन योर फ्लक्स डेंसिटी इज कांस्टेंट. So V by F ratio we have to keep constant. Here you see V by F ratio is not constant. You take the V by F and you take the VF. It is not constant. So this method is ruled out. This method is ruled out. Now this equation, we are having this kind of equation. Rather this kind of equation. This plus this. Now we want to separate it. So obviously we are left with only one option, that we have to solve the equations with the help of these data points. Are you agree with it? समझ में आ रही बात?
Yes, sir.
So whenever you get the, means in examination also, if you are getting this kind of problem, then you should make sure that whether V by F is same or not. If it is not same, then obviously graphical method you cannot use. Then you have to solve the equations. So here you can see that I have written the iron loss is in terms of all the parameters, because here flux density I'm putting it separately, not clubbing it into the constant, because it is also variable here, and the frequency and all other things again they are kept constant. Is it fine to all of you? Now here I want to explain what is the meaning of here you see 4.44 is coming because of the form factor. It is 4 into 1.11. You must have this in transformer case you must have
Yes, sir. Yes, sir. Yes.
expression over there also form factor will come.
Yes, sir.
Okay, so here you see what is the meaning of when we are taking E by F. Then if your right side BM is constant for a constant speed, so this will remain constant, means for constant, sorry, number of turns it is. So number of turns is constant, area of cross section of your core is constant, 4.44 is constant. So if flux density is constant, then E by F will be constant, ratio of voltage. So from here this concept came. Is it fine to all of you? Because if you are taking E by F, then all terms except Vm is constant. So if Vm is constant, then E by F ratio will be constant. बात समझ में आ रही है? So what is the meaning of, because E by F ratio is directly proportional to the flux density. So if flux density E by F ratio you are keeping constant, this means you are keeping flux density constant. Is it fine to all of you?
Yes, sir.
हाँ नहीं तो बोल दिया करो यार तुम लोग.
Yes, sir. Yes, sir.
नहीं समझ में आ रहा बोलो, नहीं समझ में आ रहा है. चुप रहना तो कोई बात है ही नहीं, डिप्लोमेसी है ये तो। और यू डोंट वांट टू लर्न एनीथिंग। अब ये दो इक्वेशन हमारे पास आ गई। अब हम आपसे ये पूछना चाह रहे हैं, हाउ विल यू सॉल्व इट, एंड आई वांट दैट यू सॉल्व इट, एंड आवर ऑब्जेक्टिव इज टू फाइंड आउट hysteresis and eddy current loss at 50 hertz as well as at 40 hertz। जी, अब आप बताइए। आई वांट दैट ऑल ऑफ यू शुड सॉल्व इट। सॉल्व करके बताइए। Problem, equation solving problem. Now I ask you to, here in this case f1 is 50 hertz and f2 is 40 hertz. I need your comments. I'm waiting for your comment. You are required to solve it, but I want your comments. Acha, tell me.
Sir, I want to ask, sir, number of turns and area of cross section will be same for both the cases.
Number of?
Sir, I want to ask, sir, number of turns and area of cross section will be same for both cases.
Yes, that's why it is not visible here.
Okay, sir.
Everything is same, constant. Only which here why you are going into the area of cross section and number of turns. Here area of cross section and number of turns are not here. You are required to solve these two equations. By solving these two equations, what is your objective? To find out the hysteresis and eddy current loss. आपको ये इक्वेशन सॉल्व करनी है हिस्टेरेसिस और एडी करंट लॉस को मालूम करने के लिए। हाउ विल यू सॉल्व इट? सॉल्व कर सकते कि नहीं कर सकते?
सर हो तो जाएगी, लेकिन सर उसके लिए हमें फिर सिर्फ दोनों मैग्नेटिक फील्ड के लिए सर हमें प्रोपोर्शनैलिटी कांस्टेंट एक नया इंट्रोड्यूस करना पड़ेगा, जिससे सर मतलब
इसमें कितने अननोन है ये
आ
बताओ
जाएगा
पहले
टर्म
मुझे।
का।
ये बताओ कितने अननोन है?
सर अननोन तो सर मैग्नेटिक फील्ड है BM1 और BM2 और सर प्रोपोर्शनैलिटी कांस्टेंट KE और
कितने
KH।
अननोन हो गए?
सर 4।
और कितनी इक्वेशंस हैं?
2।
सॉल्व हो जाएगी?
नहीं।
तुम तो कह रहे हो सॉल्व कर लेंगे।
सर हो जाएगा अगर सर हम लोग
हो जाएगा।
V is directly proportional to B maximum मान के B maximum square और B maximum 1.6 मान के चले तो वैसा वाला। और सर हम लोग उसको
वेरिएबल्स कम कर सकते हैं, जो नोन है उसको कम कर सकते हैं, क्योंकि दो इक्वेशन है। दो इक्वेशन है तो कितने अननोन मालूम कर सकते हैं आप?
हाँ सर कर तो सकते हैं।
कर सकते हो तो बताओ क्या?
आई विल ट्राई सर, आई विल ट्राई।
नहीं, यू कैन नॉट ट्राई भाई। दो इक्वेशन है तो दो अननोन मालूम कर सकते हैं, ये तो मैथमेटिक्स है भाई।
हाँ, तो दो इक्वेशन है तो दो अननोन ही मालूम कर सकते
तो
हैं।
यहाँ तो चार अननोन है, तो ये कैसे सॉल्व करोगे?
4 को 2 करना पड़ेगा सर।
तो कैसे 2 करोगे?
हाँ सर, हाँ वही मैं बोल रहा था कि सर वो जो
चलो
Sir, वो
This particular feedback I require, I want. Here we will solve it very judiciously. Our objective is not to find all unknown coefficients. हमारा ऑब्जेक्टिव ये नहीं है कि ये जो जितने कोफिशिएंट हैं उसको मालूम कर लें. हमारा ऑब्जेक्टिव है टू फाइंड आउट द हिस्टेरेसिस एंड एडी करंट लॉस. तो अगर हम if we are able to find out these two together and these two together, not separately but together, then and we can define this and bm1, and we can make a relation between bm1 and bm2. So our equation will have only, means we can define bm2 in terms of bm1. So we will have only two unknowns, this and this. And if we are able to find out this together, then obviously we can calculate by multiplying the frequency, we can calculate the hysteresis loss, and if we eddy current loss, and if we can find this together, then we can by multiplying the frequency we can find out the hysteresis loss. And then we are having a relation between bm1 and bm2. So from the known value of this we can find out the for bm2. That's what we have done. You try to find out. It is done very judiciously. So here you can see that from this equation, the flux density into frequency is directly proportional to the EM. All other terms you look, they are constant. So that's what the product of frequency and flux density is directly proportional to the excitation. So it is directly proportional to 250 and it is directly proportional to 100. And we took the ratio of it. So we are able to, you see, very judiciously, we are able to establish the relation between these two flux densities because frequencies are known. So we found that bm1 is equal to 2.5 times bm2. It is 2 times bm2 here, this. Now you see those equations are converted into the previous, these equations are converted into the, now you see we are having all in terms of bm1. So now we are having only two unknowns if we are clubbing these two together. So we will solve this equation to find out ke bm1 square and kh bm1 to the power 1.6. Is it fine to all of you? Now this equation, it is possible to solve these two equations to find out these two coefficients. Is it fine to all of you?
Yes, sir.
Yes, sir. Yes, sir.
Now it's easy. You can solve. I can solve. Anyway, it is solved, and then we are able. These two equations are solved, and we are able to find out the value of ke bm1 whole square is 0.049 and kh bm1 1.6. Once you are able to find these two, now it is easy. You know, at the 50 hertz, eddy current loss is equal to this. So we are putting this together and multiplying by square of the frequency. We are getting your eddy current loss at 50 hertz from the test result, and your hysteresis loss. And just to check that your answer is correct or not, you sum these two. This sum should be equal to whatever you are getting here. It should be equal to 200 watt at 50 hertz. Similarly, for other one here, this is for the 40 hertz. Another equation bm2. You can do both ways. You calculate bm2. We are putting directly here. You can see here in this equation because you know the relation, so you can find out the bm2 in terms. Anyway, this this is basically the 4 times you divide KEBM1 by 4, then you will get this value. That's what I have done. This is KEBM1 square value of KEBM, and we are dividing it by 4 times, and then frequency square of the frequency, we are getting the eddy current loss. And similarly, to the power, we are dividing the KHBM1 to the power 1.6 by 2 to the power 1.6, we are getting this value, and then we are multiplying by this 40. So and you sum together, it should be 40 watt. So this is how equations are solved using data points. And you should be very careful. The main thing, if you are doing, obviously if you are doing using graphical method for this, it will not be correct at all, because your flux density is variable, and your plot will never be a straight line. If you are plotting somehow, means using these two data points is plotting, because you are having a two variable relation, and then you have to solve it. And then solving also, you should be very careful, judicious, and full of the knowledge. Only then relevant coefficients values you will calculate, and then you will ultimately converge to the solution. If anybody is having any question regarding this example, you can ask, please. अभी कोई क्वेश्चन है किसी का? नहीं है? Should I move?
Yes, sir. No question.
Now, this is graphical method. I want that on the next turn, everybody should bring a graph paper, and we'll solve this problem on a graph paper. Then you will be able to understand how it is done. So this one I am not taking today. We will take it on the next turn, and you all of you should bring a graph paper with you, simple graph paper, and we'll solve it. Now, one of the method, you see, one of the method, we are able to discuss. We discussed one thing, that how can we separate the hysteresis and eddy current loss, and that we have done. Means you can solve the equation, or you can find out the graphic. You can separate it graphically also. Conditions you are already aware of. You need experimental data for both the methods, whether you are solving the equation or you are separating it using graphical method. In both the cases, you need the data points, experimental data points, and these experimental. So now another thing is that how can we measure the core loss? One thing is, once you are able to measure the core loss, only then you can think of separating them into the hysteresis and eddy current loss. Now how can we measure the core loss? जी बता सकते हैं? Core loss, obviously core loss will measure in the magnetic sample. So how can we measure the core loss? Any idea? Core loss or iron loss? भाई आप तो कर चुके हैं इस एक्सपेरिमेंट को. ओपन सर्किट टेस्ट करते हैं ट्रांसफार्मर पे.
Yes, sir. Yes.
तो वो एक मेथड है. इफ यू आर गेटिंग सम कोर, मैग्नेटिक सैंपल कोर के फॉर्म में ही होगा, तो हम क्या करेंगे, उस पर एक प्राइमरी वाइंडिंग कर देंगे, एक सेकेंडरी वाइंडिंग कर देंगे, और ओपन सर्किट टेस्ट परफॉर्म कर देंगे, हमको कोर लॉस मिल जाएगा. है
Yes, sir.
ट्रांसफार्मर
Yes, sir.
में प्राइमरी और सेकेंडरी वाइंडिंग होती है, 2 वाइंडिंग्स होती है, LV-HV वाइंडिंग होती है, तो उस पर हम परफॉर्म कर लेते हैं. लेकिन अगर कोई सैंपल आपके पास आया, और सैंपल ही आते हैं टेस्टिंग के लिए, मैग्नेटिक सैंपल, तो हाँ उसके और लैमिनेशन फॉर्म में होता है, जो यूजफुल सर्किट होता है एडी करंट रिड्यूस करने के लिए, तो हम उसका बंडल बना लेते हैं, और उसके ऊपर हम ओपन सर्किट टेस्ट परफॉर्म कर लेते हैं और उससे हमको ये मालूम हो जाता है कि इसमें कितना कोर लॉस है। और उसके बाद अगर आप इंटरेस्टेड हैं हिस्टेरेसिस एडी करंट लॉस मालूम करने के लिए तो आप ये मेथड यूज कर लीजिए। आर यू फाइन?
Yes, sir.
Yes, sir.
Now another method is AC bridge method for measurement of iron loss. Because that the open circuit test actually that is called basically wattmeter method, testing method, but it is basically open circuit test. This is open circuit test kind of test is performed on the bulk sample, but if many times you'll find the samples when you are working at a very high frequency, so the ferrite cores are used and basically they are not available in bulk form. Then high frequency excitation is another issue. Then you require high frequency wattmeter and all these things. Then AC bridge method is used. So you can see that AC bridge or bridge methods are very powerful methods, very versatile, you can say. It is used in many things. You must have seen that it is used for measurement of inductance, capacitance, frequency, mutual inductance, and then it is used for quality control also, है ना? For insulation testing and tan delta मालूम करते हैं, and then for means स्टील शीट की का इंडक्टेंस मालूम कर लिया और उसका फिर रिएक्टेंस मालूम कर लिया, then by that we can find out whether it is having any defect in it or not. So this is bridge circuits are used for many applications. Then another application here you can see that you can measure iron loss also, and it is very interesting. So if you look on the bridge, it is like a Maxwell's inductance bridge, inductance comparison bridge. It is that only. Here, this is your sample, and this is your core, whose loss we are interested in finding out, iron loss or core loss in this. So obviously, whatever at whatever frequency you want, then that frequency supply will use here. And this is your bridge. This is your variable arm. And for this sample, because this sample will have obviously inductance as well as resistance, and number of turns are known, its cross-sectional area is known, all these things are known, and you balance the bridge. Then obviously when you will balance the bridge with the bridge balancing equations, you can find out the sample inductance and sample resistance. This is what I have done, means the bridge balance equation, and that you are already familiar with. So you are able to find out these two equations. One equation is giving you the resistance of the sample, and this is giving you inductance of the sample. But this is not our objective here. Here our objective is to find out the core loss that is occurring in a sample at a particular frequency. Now that part we are doing, whatever till now, whatever with the conventional thing we can do with the bridge, that we have done. So now we are aware of the sample resistance and we are aware of the sample inductance. Beyond that, the iron loss in the sample is given by whatever loss that is taking place, because you know this sample resistance into I1 square, because current I1 is flowing through it. This I1 is flowing when the bridge is balanced, and I2 is flowing here. So RS I square 1 RS represents all the losses that is occurring in the sample minus winding resistance, whatever winding that is wound on the core. This resistance by DC test we can find out. So if we'll minus this loss, then winding copper loss is subtracted from the total loss that is occurring in the core. So remaining loss will obviously the core loss. Now this total current is equal to I1 here. Total current from the supply is I1 plus I2. total current is I1 plus I2, and from the balance equation we can write I2 is equal to, from here you see, I1 upon I2 is equal to R plus here from here, sorry, from here. The balance equation, it will be balanced only when I1 R1 is equal to I2 R2, and I1 ZS is equal to I2 Z, you can say Z here. So that's what I had written here. So from here, you can see that I1 upon I2, I1 will be equal to R2 upon R1 into I2, or I2 is equal to R1 upon R2 into I1. So that's what I substituted here. Instead of I2, I'm writing I1. So here the I1 we are taking common, and so with this we can write I1 in terms of I, total current. So that's what here we have written. So you can see that we'll replace, because I1 it is, although we can measure, but we are not measuring I1 generally, because that will modify your, if I'm putting ammeter here or ammeter here, that will modify your branch impedances. So we are putting, so we are only aware of the total current, not the bridge branch arm currents. So we converted it into the I1 into the total current, that reading we are having. So this is modified to this I square, because we can write I1 square. So I1 square is written as I square R2 plus R1 plus R2 whole square RS minus. So this way you can find out experimentally, you can measure the iron loss in a core which are not suitable to be tested as an open circuit test here, because of the small cores and all, and high frequency excitation is required. So this is done through the bridge, and this is a standard method. So this is how iron loss is. If anybody is having any question regarding this, you can ask. By the time I'm taking your attendance, you go through it and try to absorb and understand. If you're having any question, you can ask. Rule number 1 is method for measurement of core loss. And if you are having any question, and I want that you should go through your open circuit test and try to find out the intricacies of that. If you are having any question regarding that also, I'll address that. Okay. Okay, thank you.